Hello, organic chemistry. In this lab, we will be preparing a simple ester, isopentyl acetate. Due to the type of chemicals we'll be working with, the entire setup and operation of the experiment will be performed in the fume hood. So what I have set up here today is the materials we'll need: the chemical, sulfuric acid, glacial acetic acid, isopentyl alcohol, silica gel, calcium chloride, and some glass wool materials to make what's called the calcium chloride drying tube. So the setup I'll explain as we proceed with preparing the reaction. Includes using a microscale 5 milliliter conical vial, that will heat on the aluminum heating block. Within that, we can also put a miniature magnetic spin vane. So just like a magnet on a stir plate, this little magnetic spin vane is V-shaped to fit in the bottom of the conical vial. And then we'll also prepare what's called a calcium chloride drying tube. And the purpose of that is so that when the reaction is heating, water vapors from the air don't get into the reaction, because they would cause the reaction to proceed to a lower percent yield. So to prepare the simple calcium chloride drying tube, that's the first thing I need to do to get the setup ready. We just put a little bit of glass wool for starters in one end of the tube. Doesn't really matter how much, just enough to be in there to hold the calcium chloride in place. And to get the calcium chloride in there, I'll use a little scoop of and all this is, the calcium chloride, is a drying agent that absorbs moisture from the air. And it also would absorb moisture that's created in the reaction, so it doesn't return back to the reaction. So the glass wool is just there. It'll be a little bit on both sides to keep the calcium chloride beads and pellets contained inside that tube. Doesn't have to be pretty. It just serves the purpose of holding the materials in place. So that will attach directly to what's called a water-jacketed reflux condenser, and I'll explain that. The water-jacketed reflux condenser, and if you look at the picture that will show it as well, has a tube on the inside. It's kind of hard to see, I'm sure, in the video, but it has a tube on the inside that allows vapors to go up inside, and then on the outside, the jacketed part allows water to go in one side and out the other side. So that water coming in and circling through that outside of the tube that's on the inside allows the vapors to condense and drip back down into the reaction vial. So as the reaction proceeds, the vapors, the solvent, remain. So I'm going to put that aside for now, and I'll finish setting it up after I add the rest of the reactants. So I always do my reactant prep, my chemical measuring, over a tray. So in the reaction, I'm going to use an autopipetter that measures out precisely 1 milliliter of reactant. And what you'll have to do is look up the density of isopentyl alcohol to figure out the mass of isopentyl alcohol used, and use that to later figure out the percent yield based on the mass of product that's created. So then we also added to the reaction file a small amount of SiO2, or just essentially silica. And what that does, that absorbs moisture in the reaction so that it doesn't impact the product creation. So I put just a small amount in there. It says about 0.3 grams, and I just used, kind of eyeballed about 0.3 milliliters to assume it's close to 0.3 grams. So then next I'll add the 1 milliliter of isopentyl alcohol. Then an excess 1.5 milliliters of glacial acetic acid, and for this I'm just going to use the graduations on my plastic pipette, because this is going to be an excess, so it's okay if it's a little over. And then lastly, we'll add sulfuric acid that catalyzes the reaction to proceed. So our two reactants, isopentyl alcohol and acetic acid, will combine to make the isopentyl acetate. So sulfuric acid, all we need now is just about 4 drops. There we go. So all of our reactants are set. And then I'll add the magnetic spin vane. So everything is in there, all of our reactants. And then lastly, I'll attach the reflux condenser. I'm going to put that on my aluminum heating block and start the heating. And it's always important, things like this, to clamp them. So I'll get in close there so you can see I have the magnet spin vane going. It's spinning rather slowly for now, just so you can see it moving. I'll speed it up some. So we got all of our reactions mixing. So right now I don't have the water hooked up, but I soon will, so that our apparatus looks like the diagram shown here, with the water-cooled reflux condenser with the calcium chloride drying tube attached. So you'll see that the water goes in the bottom and comes out the top. And again, that all helps keep the solvent and reactants liquefied so they continue to react until the reaction process is complete. All right, so our reaction has proceeded for about 45 minutes now. So I'm going to take it apart, and in the next steps will be what's called the isolation and purification of the product. So in those steps, we'll take the whole assembly apart, and then we'll add ether, which allows the product to dissolve in the ether but not the reactants. And then we'll also add about 2 milliliters of 5% sodium bicarbonate, which will cause any excess reactant to be neutralized So then anything that's water soluble will stay in the aqueous layer associated with the bicarbonate solution, and our product, the isopentyl acetate, that's not water soluble, will be collected in the organic layer. So once I get this apart, I'll start over again and show you the transition to isolating, and then we'll move on to the distillation to purify the product. Alright, so I have the vial removed from the hot plate. I've let it cool a little bit. Then the next step would be to take out the with tweezers, take out the little magnet. And those are pretty expensive, so be careful not to lose them. We'll wash everything in a little bit. So the next I'm going to add about a milliliter of ether, and I'm just going to use the graduations on the vial. A little excess is fine. And then we'll add a few milliliters of our sodium bicarbonate solution. And what you should see is some fizzing, a little fizzing at the bottom there. It's okay to add more. So let that sit for a few seconds while I get the glassware ready for the next part. So in the next part, we're going to transfer the product material to a new 3 milliliter conical vial. And if you look very carefully, it's hard to see it for sure in here, but there's actually two layers. We have an aqueous layer, and then we also have the organic layer on top with the ether and our product. So what I'm going to do is just carefully remove just the organic layer. And it's okay if you get a little water in there, we'll dry it during the distillation setup. So there's our non-purified product. So to purify the product, I'm going to come back in a second with a different setup and I'll explain that. We're going to do a distillation to purify the product. Alright, so for the purification process, what I've done actually, I went through and did 2 more additions of ether and a few more additions of sodium bicarbonate and extracted those layers to add to our unpurified product vial. Then, because the ether is very volatile, I put it back on the hot plate. The hot plate's still at about 90. If I look at my thermometer, about 95, and that allowed all the ether to evaporate away, but the product boils at a much higher temperature, so it didn't dry away. But the water part would not have easily dried away. So what we do to absorb any excess water before we start doing the distillation, I can add a little bit of what's called a drying agent, in this case sodium sulfate. So the sodium sulfate drying agent just absorbs any last bit of moisture that was present from doing the organic extraction with the sodium bicarbonate. So I try my best to leave behind all the aqueous layers and only get the organic layers, but there's always going to be a tiny amount of water that carries over. What we do now, I can set it up with the distillation head. Screw it on there. And as that warms up, what I'm going to do is set it up with another thermometer in the center. And when I come back, as the distillation is proceeding, I'll explain how we can also measure the boiling point as the reaction proceeds. So what we'll do with this, if you look at the diagram in the picture that I'm going to show separately, the side of the distillation head has a curved lip on the bottom of it down here. So as the liquid evaporates and condenses and collects into that little rim, that's where we actually collect the product. And since we're heating it at a pretty high temperature, we want all of our organic product to recollect into the distillation flask. So to help with that, I'm going to put the reflux condenser back in. We don't need the calcium chloride drying tube. And I'll set the reflux condenser back in. So now what this will do, it will allow any product vapors that go too far up in there to recondense back down and collect in the curved part of the Hickman distillation head. So I'll come back in a minute and I'll explain and show the product collection. The sample's been heating now for probably about 20 minutes. It's taken quite a while for the vial and the contents and the apparatus to get warmed up. So I'll zoom in a little bit. You can see the contents in the vial are boiling, bubbling in there. And then what I also have set up in the apparatus, I have the what's called Hickman distillation head, which is this part in the middle. And then I have the reflux condenser again running with water. And then on top I have a thermometer that, if you look carefully, the thermometer tip is right down here above the collection neck of the Hickman distillation apparatus. So as this proceeds and we start to collect some of the liquid, some of the vapor as it rises will condense on the tip of the thermometer, and that's how we can collect a boiling point of our product. I'll come back in a few minutes once we start collecting some liquid and show you how the temperature of the thermometer in the middle there has changed to measure the temperature of the vapors condensing, which corresponds to the boiling point. Alright, so the distillation process has proceeded probably another 20 minutes. It probably takes about an hour total to do the distillation. Some things I've added here, I wrapped the bottom of the setup with aluminum foil. It just helps keep the glassware in the lower part warm enough so the vapors can rise up into the condensation area where we want them to condense. You can see the thermometer, it's been hovering between about 140 to 143. So we can accurately read that the boiling temperature, I'm going to say, is 141.8, 142 is good. And then if we look really, really close at the distillation collection head, you can see where the liquid is in the little neck here. So the next step is I'm going to turn it all off and let it cool, and then we'll collect the liquid and mass the amount of liquid that we've created. All right, we're back now at the balance area. We have our product in just the Hickman distillation head. So again, if you look carefully at that, you can see the little bit of liquid in the bottom of that lip. And that's what we're going to collect with the glass pipette. So we're going to collect it into a small conical vial. So I pre-masked the vial. I'll give you that information in a minute. And these have little increments on them, which helps us with the process. So all I'm going to use is a glass pipette, and you can put it down inside the vial, draw out the liquid, and add it to the vial. I'll try to get a little bit more out of there. The last bit. It's hard to collect every last bit from the distillation process unless we do this several times. But we started with a milliliter of reactant, and our product is actually a higher molecular mass. So we should have less than a milliliter, or roughly less than a gram. So we have a total the vial itself weighed 19.1246 grams, and with the product it's 19.7002 grams. So what I'm going to do next is I'm going to prepare a small vial of sample for injection into the mass spectrometer. So all I have in my capillary here is a very tiny amount left. It doesn't even take but just a smallest of drop of product. So that's probably even way too much in there. So then, to prepare our sample for the mass spectrometer, we dissolve it in hexane. So I'm going to use a new glass pipette and add solvent hexane. Usually add about a milliliter. So now we'll go over to the mass spectrometer, and I'll show you more about that and get a sample going. So here's our mass spectrometer, and the last step to do the sample prep, I need to put a cap on my capillary vial. So the mass spectrometer, here's the capped vial. Has an auto sampler. So the auto sampler has vials to wash the needle with hexane and then inject the sample for us. So overall, as you learned about in chapter 12, the mass spectrometer has the gas chromatograph side to separate out the compounds, the mass spec side for the analysis, and then over here on the computer we'll have our data. So what I'm going to do is I'm going to download the program and run the sample. And it takes about 10 minutes for this sample to run. So I'll come back and show you the data and how to analyze the data when this sample is done. So what I'm showing you now is just the auto injector. If you can see in there, there's a very small needle, and what it's doing is it's washing the needle with a solvent, hexane. It does 3 washes, and in our sample vial that I put in the little tray, we'll move over, and then what it will do is it will extract exactly 1 microliter, inject the 1 microliter that goes into the gas chromatograph for the separation, and then as compounds come off the mass spectrometer, or pardon me, off the gas chromatograph into the mass spectrometer, they'll be analyzed for both qualitative and quantitative amounts. And that takes probably about 7 minutes for the run to show our product, so I'll come back when the data is finished running. Okay, the sample's still running, and I know the screen here might be hard to see all of it recording, but hopefully what you can see there is one really big peak. So what's happening again in the gas chromatograph is the sample is passing through the column, and based on differing boiling points, different compounds pass through at different rates. So we can see one big peak there, and what I can do is go to the qualitative side of the software, and now it's a little bit more zoomed in. If I zoom in a lot on what's called the gas chromatograph side, we can see a lot of other little peaks. And those little peaks are probably impurities. And what we can also do, what's really cool, if you recall from the theory of mass spectroscopy, we want to look at the positive ion fragments. So what I'm going to do is just say, I want to analyze those positive ion fragments and look at what is this peak around 3.2. And I can do a similarity search. And the similarity search says that it's methylbenzene, 84% chance, or toluene. And to me, what that probably refers to is a little bit of impurity in my hexane solvent. The important one, if I unzoom now and focus on just my one big peak in the middle of the screen there, and again I can say in the software I want to look at just the positive ion fragments. I'm going to select that whole peak. I can also subtract out some of the background to make it more accurate. And now I go back down here to the mass spectrum. If you look in the bottom of the screen, the long box here shows the mass spectrum, and you can see all the different fragments. And if I right click and do what's called a similarity search, now what it shows me is pretty good chance. In this case, the similarity search is showing 98% chance that my compound is 1-butanol 3-methyl acetate, which is in essence isopentyl acetate. So if you look down here, you can see the structure of the library match being isopentyl acetate. So that's a good thing. I'm going to go back to the gas chromatograph side of the spectrum, and again, here's the original GC spectrum showing that one big peak in the middle that's filling up pretty much the whole entire screen. And if I zoom in, I can see that there are a variety of smaller peaks. So these small peaks would commonly refer to some kind of impurity that were probably in the solvent. And because they're so small relative to the main peak we're looking at, we can say that the purity of our product is very good. So in the mass spectrometer, the gas chromatograph mass spectrometer, this is the kind of analysis you can do for many different types of samples. The challenging part is how do you get the sample to be able to be injected into the gas chromatograph, and commonly you have to do different kinds of solvent extractions. For the rest of the lab, you'll have to look at and analyze the data. We have the mass of reactant, or pardon me, the volume of reactant. So you'll have to look up the density of isopentyl alcohol to figure out the mass of isopentyl alcohol used. Then we have the mass of vial, then the mass of vial with sample. So you have the mass of product, you can calculate the mass of reactant, and from that calculate percent yield. Then we also have, in the handout, was the IR spectrum. So we could acquire an IR spectrum for the sample, but for time's sake, I'm going to ask you to refer to the spectra in the handout. And again, here's our IR spectrometer. I could put a different sampling apparatus on there and very easily measure an IR spectrum of both the reactant and the product. Thank you for tuning in. Here's the classroom in case we ever get back here. Hope you have a good day.